Shaitan Rajim, Bismillahir Rahmanir Rahim. Dear student, Assalamu Alaikum. Today, what we are going to do, explain you now. A bit. Class 9, subject physics. Chapter we are doing 7 properties of matter. The name of the chapter is Properties of Matter, and it is 7th chapter number 7 of 9th class. Topic of today's lectures will be 7.5. We will try to cover 7.5 topic. Pages covered today's lecture will be 151, 152, 153, 154, and 155. These pages we will try to cover. Okay, I repeat, class 9, subject physics, chapter number 7, as we were doing. Properties of matter, this is the name of the chapter, and topic of today's lecture is 7.5, and pages covered from 151 to 155. Please start from 151 page. This is the chapter we are doing, unit number 7, properties of matter, and we are on topic 7.5, which is pressure in liquids. This is on page number 151. If you open 9th class textbook, 151 page, you will find this topic, pressure in liquid. We are going to start pressure in liquids. First of all, I will tell you whenever the liquid is placed in a container, it will exert some pressure. Whenever the liquid could be water, whenever the water is placed in a container, it exerts the pressure on which it is placed. The pressure of a liquid acts in all directions, and this pressure acts in all directions. As I have explained you earlier on, where when I gave you the example of balloon, so atmospheric pressure acting from outward, and the air inside the balloon will also exert the pressure. When these two pressures are equal, so and I gave you the example of the air bubbles as well. As long as the pressure inside the air bubbles and the atmospheric pressures are equal, they will expand, and when they are not equal, they will burst. So similarly, whenever the liquid is placed in a container, it exerts pressure on the wall of the container, and in all direction, it will exert the pressure in all direction. Uh, we use a device which is called the pressure sensors to measure the pressure inside the liquid. To measure the pressure inside the liquid, we use a device which is called pressure sensor. We find that pressure of the liquid varies with the depth of sensor. So as we goes on increasing the depth, the pressure will be vary. It will vary. It will not remain constant. It will keep on changing. Now consider, look at the picture 7.3, figure 7.3. You can see this is the big container and there is a small container inside it. There is a big one, this one is the big one, and the small one is placed inside the liquid. Okay, this is immersed. This is partially immersed in the water. So suppose this one, gray one, is the area or base area of the small container. And the pressure will be exerted in this direction, and the depth from this from the bottom to the top one is denoted with H. So we have a pressure which is exerted downward direction, and the area is the gray color, gray bottom of the vessel, which is denoted with capital A, and the depth is denoted with capital H, because small h, because it has been immersed into the liquid. So I repeat, this is the bigger container, this one which my cursor is pointing out, and this is a small container where my cursor is pointing out. Okay, when it is partially immersed into the water, this is the liquid, this is all the liquid. When it is partially immersed in the water, It will exert a pressure, and the pressure will be exerted in all directions. Let's suppose A be the area of the small container, the capital A be the area of the small container which has been immersed, and P be the pressure, and H is the depth under which it is partially immersed. Okay, the depth it is partially immersed. So how we can find the mass of the liquid cylinder? Mass of the liquid cylinder is denoted with small m, and you know the density formula is mass per unit volume. Since I am using the same formula, density is equal to mass per unit volume. But in this case, we want to find out mass. So density will be multiplied with volume. I repeat, density formula I'm using. Density is equal to mass per unit volume. Since I want to find out mass, so density by cross multiplication with density multiplied by volume, you will get mass. And the volume, how can we obtain the volume? A is the area of the bottom of this cylinder, and when this is multiplied with small h, you will get volume. And when volume and density is denoted with rho, density is denoted with rho. Density of this liquid is rho. So mass I can obtain with the formula volume multiplied by density, and volume is if you multiply bottom capital A with depth, you will get the volume, and the density is denoted with rho. Now you know this force acting on the area A. Force acting on a force, formula of the force is F cross. F is equal to W, W is equal to mg. This is the formula. This is the formula for F is equal to W and W is equal to mg. So you know this mass is I just found in my last equation. Mass is given. I found it A cross H times rho. Just put the values of mass over here. Mass is AH times rho, and G is in the formula. Because I use the formula F is equal to W and W is equal to mg. And the mass value is AH rho, which I just found, which is mass is equal to AH times rho. I just put the mass value in this equation, in this formula F is equal to W, W is equal to mg. And mass is AH rho, or G is the acceleration due to gravity. Since now we want to find out the depth, so pressure formula is, we have already discussed this formula, pressure is equal to force per unit area. And we know the force is, we just found AH rho times G. Just put F is equal to F AH rho G, this one. I'm putting this one on instead of F. F is equal to AH rho G, and A will come down. This A will be cancelled with this A. So my liquid pressure at depth H will be P times rho GH. Rho GH. Equation 7.3, this is called equation 7.3, gives the pressure of the depth H in a liquid of density rho. It shows that the pressure in a liquid increases with depth. So since pressure and since pressure and H have this directly proportional, they are in front of each other. So if the depth increase, the pressure will also increase. If we have a more depth, we have a greater pressure because they are both directly proportional. That's why he's saying it shows that the pressure in a liquid increases with depth. As we keep on increasing the depth, the pressure will also increase. So liquid pressure at depth H can be found with the formula P is equal to, capital P is denoted with pressure. Pressure is equal to rho GH, where rho is the density and G is the acceleration due to gravity, and H is the depth. I repeat, we found the pressure in the liquids. So we found the pressure P is equal to rho GH. How did we find this? We have two vessels. One is a bigger one, and the one is a small one. So this small one is dipped into the water in a liquid. It is partially dipped. So the area of the bottom of the small vessel is denoted with capital A, and the P is the pressure, and H is the depth. It is noted with depth, a capital A, small h. So how we can find the mass? We can find the mass is equal to volume times density. I use the same formula, density is equal to mass per unit volume. So if I want to find out the mass, just multiply volume with density. You can find it. You know the volume. How can we calculate the volume? By multiplying capital area A, the bottom of the liquid is A, area A, and if it is multiplied with H, it will give you the volume. And density is denoted with the letter rho. I use this formula as I know F is equal to W and W is equal to M times G. I just substitute the values of M. M I just found in my this equation. M is equal to AH rho. So I put this M over here and G will be as it is. The G of this one, M I just put the AH rho and G will be as it is. And the formula for pressure is equal to P is equal to F over A. As we have already discussed this formula, pressure is equal to force per unit area. And force is AH rho G. I just put force is equal to AH rho G in this equation. P is equal to F over A. And this A will be as it is, and the bottom. This A will be cancelled with this A. So what will be left? Pressure is equal to rho GH. Rho, because this A has cancelled with this A. So what is left? H rho G. So my pressure and depth, H is the depth. So they are in front. They are directly proportional. If we increase the depth, then the pressure will also increase. Look, it shows that the pressure in a liquid increases with depth. So liquid pressure at depth H can be found P is equal to rho GH. So P and H are directly proportional. Increasing the depth will increase the pressure. This because other two values are constant. Density is constant and the acceleration due to gravity value is constant. So what is only thing is varying? Increasing the depth, the pressure will also increase. Now I'm moving towards Pascal's law on page number 152. If you open page number 152, you will find Pascal's law. First of all, I read the statement of the Pascal's law or the definition of the Pascal's law. Pressure applied at any point of a liquid enclosed in a container is transmitted without loss to all other parts of the liquid. Pressure applied at any point of a liquid enclosed. Look, this is the container. It has small holes inside of it. When we apply the pressure over here, right? When we apply the force over here, it will exert the pressure, and the water will come out of the holes equally. It will be transmitted equally in equal amounts because the hole size are same, right? So we have how many holes? 1, 2, 3, 4, 5, and 6. When we apply the force over here, force on the water, on the liquid, with the help of the piston, it will exert the pressure and the pressure will be transmitted equally in all directions in the enclosed container without any loss to other parts of the liquids. So it can be demonstrated with the help of a glass vessel having holes all over the surface as shown in figure 7.14. If you look figure 7.14, you can understand the Pascal's law with the help of this diagram. With the help of this figure 7.14, you can understand the Pascal's law. It can be demonstrated with the help of the glass vessel. This is the glass vessel having holes all over its surface. You can see the holes 1, 2, 3, 4, 5, 6. There are the 6 holes in the vessels. You can see this all over surface. Fill it with water. Fill this container with water. Uh, so push the piston. This is the piston over here. So this is the piston. This one is the piston. So if you push the piston, the water rushes out of the holes in the vessel with the same pressure. The water will rush out of the holes. Water will rush out from this hole, this hole, this hole, this hole, all holes with equal same pressure. The force applied on the piston exerts The piston exerts pressure on water. This pressure is transmitted equally throughout the liquid in all directions. So this pressure will be transmitted in equal amount from all the holes in all directions. Okay. So this is the applications of the Pascal's law. So you can demonstrate this example, Pascal's law, with the help of this diagram, with the help of this figure 7.6. So I repeat, there is small vessels. It has holes in all direction. When we applied the force over here, it the on the liquid, it will exert the pressure, and the pressure will be transmitted equally, or the water will rush out from the holes equally in the same direction. All holes equally. Okay, so this is the application of the Pascal's law. Now the point is where and Pascal law is hold for fluids. When you see the word fluid, it means both. Pascal's law is true for both liquids and gases. So fluid means liquid and gases. I repeat, fluid means liquid and gases. So instead of liquid over here, we can have a gas as well, because Pascal's law is hold for both liquid and gas. Now we study the application of Pascal's law, where the Pascal's law is actually applying in our daily life. Pascal's law finds numerous applications in our daily life, such as automobiles, hydraulic brake systems, hydraulic jacks, hydraulic presses, and other hydraulic machines such as running to the 7.15. You can see this is a 7.15 hydraulic excavator. This is used uh, to throw the rubbish, the big things, or to big things very easily from one place to another. So this is called hydraulic excavator. Hydraulic excavator works on the principle of Pascal's law. So, so all the automobiles, hydraulic brake system in the automobiles, in the buses, in the cars, they work on the principle of Pascal's law. Now we study the hydraulic press and how it works. So hydraulic press is a machine which works on the Pascal's law. It consists of two cylinders. You can see this is the hydraulic press. So it consists of two cylinders. One is a smaller cylinder and one is the bigger cylinder. The area of smaller cylinder is small a, and the area of the bigger cylinder is capital A. So you know this, I applied the force on the smaller piston. So smaller piston has a small area. So you have discussed this pressure, that there is a inverse relation between pressure and area. If we have small area, the pressure will be exerted more. So, so there is a indirect proportion between pressure and area. If we have small area, it means that more pressure will be exerted. So that's why I am applying the force on the smaller. If you can see the direction of the force, here the force is applied. The force will be applied on the smaller piston, and there is a fluid inside, there is a liquid inside. So when I apply the force over here, the this piston will be moved upward. You can see the direction of the arrow. This piston will be moved upward because a great pressure will be exerted because due to the small area of this piston. So lesser area, more the pressure will be exerted. Cross-sectional area of figure 7.16. They are fitted with piston of cross-sectional area A and A. The area of small piston is small a, and the area of the bigger piston is capital A. The object to be compressed is placed over the piston of large. Here the object is compressed. The object which is need to be compressed is placed over here. So the force F1 is applied on the piston of small cross-sectional area. Here we apply the force which is called F1 force is applied on the small piston. The force F1 is applied on the piston of small cross-sectional area A. The pressure P produced by small piston is transmitted equally to the large piston, and a force F2 acts on A, capital A, which much larger than It means F2 is much larger than F1, because here the pressure will be more, and this pressure will be equally transmitted on the other side of this piston where our body is compressed. So I apply the force over here, and according to the Pascal's law, this pressure will be exerted equally in all directions. So my this piston will be moved upward. So let's suppose pressure on a piston of small area A. You know the formula for pressure. Pressure is equal to force per unit area. Since this is the a pressure on the first piston, smaller piston. So my pressure on the smaller piston will be P is equal to F1 over small a, because F1 is the force on the smaller piston, and A is the small area of the smaller piston. So how can we find the pressure? Pressure on the smaller piston will can be calculated F1 divided by A. Now I apply the pressure on the bigger piston. The area of the bigger piston is A, and the force is F2 on this on this bigger piston. So how can we find the pressure? Pressure is equal to F2 over A. Since left side of these two equations are equal, so when the left side of these two equations are equal, the right hand side will be equal. So in this case, F1 over A is equal to F2 over A is equal to F1 A. So when the left hand side equals, the right hand side will be equal. So that's why I can write F2 over A is equal to F1 over A. Since I want to find out the force F2, which is this one, which is on the bigger piston, I want to find out the F2 to separate out. I separate this out. So A will be divided here. If it will go on the other side, it will be multiply. So A times F over A, F1 times A over A. Since this is the ratio of the areas of the bigger piston, A capital A is the area of the bigger piston, and small a is the area of the smaller piston. So this is the ratio, and since this is the ratio is a greater than 1, and its value is greater than 1. Hence, the force F2 that acts on the larger piston is greater than the force F1. So F2 is greater than the force F1. You got to remember this, because small force applied on this piston, it will generate as greater pressure because of the small area of the piston, of the smaller piston, and it will, and this force can be lift the this force is can lift this area of the bigger piston due to the larger pressure. So now with the help of using this law, we can calculate, we will solve the example 7.2 now. 7.2 example is on page number 153. If you open 153 page, you will find the example. I'm going to apply this formula to calculate F2. I will use this formula, Pascal's law, hydraulic press. F2 is equal to F1 times A over A. In hydraulic press, example number on 153 page. Now I'm going to discuss example 153 page. Example 7.2. In a hydraulic press, a force of 100 Newton is applied on the piston of a pump of cross-sectional area 0.01 meter square. Find the force that compresses the piston cotton bale placed on larger piston of cross-sectional area 1 meter square. So first of all, I will write the given data. F1 force F1 is given to me 100 Newton, which is applied on the piston of the pump of the cross-sectional area, and its area A is small a is 0.01 meter square. Next, capital A is also given to me, which is 1 meter per square, and in this numerical, I want to find out F2 by using this formula. First of all, small a is 0.01 meter per square and capital A is 1 meter per second square. Pressure on a smaller piston can be calculated. I just gave you the idea. Pressure of the smaller piston is P is equal to F1 over A. I am using this one. And pressure of the bigger piston is equal to P is equal to F2 over A. So I can calculate the pressure on the smaller piston, which is F1 over small a. F1 is 100 is given to me. F1 is given to me 100 Newton, as I told you earlier on. Now, small a is 0.01 meter square. This is also given to me. You can see in the example 0.01 meter square is a small area, and 1 meter per square is the capital area. So I'm just putting the values now. F1 over A, F1 is 100 Newton and a small a is 0.01 meter square. So if you solve this, you can find 10,000 Newton per meter, and the unit of the pressure is Newton per meter square, or simply Pascal. We can say Newton per meter square equals to Pascal. Now I want to find out the F2. How can we calculate the F2? By multiplying. If you want to calculate the F2, so P times A. F2 is equal to P times A, because F2 is equal to P times A. Use this formula. P, I just found 10,000, or area of the bigger piston is 1, as you know this. So my pressure, my force F2 on the larger piston will be 10,000 U. You can see this, as I had told you, this one F2 is much greater than F1, because you can see this in example. F1 is 100 Newton. The F2 I found is 10,000 Newton, which is much greater than F1. So hydraulic press will compress the bale with a force of 10,000 Newton. So 10,000 Newton, F2 is is greater than F1. You can see, uh, as I discussed in my lecture in the topic Pascal's law. So hydraulic press, when it's studied, the F2 is much greater than F1. You can see F2, which is 10,000 Newton, which is greater than F1, and F1 is only 100 Newton. So this is the proof of this hydraulic press. Pascal's law also apply in the braking system in vehicles. So this is the braking system of the vehicle bus. Hydraulic press brake of a car. So in our car we have in some expensive car we have a hydraulic brake system. This hydraulic brake system works on the principle of Pascal's law, based on the Pascal's law. How it works? This is the brake. You can see the figure. Figure 7.17, hydraulic brake of a car. The hydraulic brake of the car works in this Pascal's law. So it consists of this is the long tube uh, where our fluid is moved. So my fluid is moved in this long tube. So we have this front wheel, and this is the back wheel of the car. Okay. So in the back wheel we have a brake drum, and we have a piston and storing spring and brake pad. So these are the master cylinder. This is the master cylinder. This is the piston, which is called a master cylinder, and this is also the piston over here. So these are the pads and this. So this is the hydraulic brake of a car, and hydraulic brake of the car works on the principle of Pascal's law. The braking system of cars, buses, and etc. also works on the Pascal's law. And as I have already told you, the hydraulic brakes as shown in figure 7. This is the hydraulic brake system 7.1. Allow equal pressure to be transmitted throughout the liquid. You can see when the brake pedal is pressed, so the pressure of the liquid will be exerted throughout the liquid. Throughout the liquid. This is the Pascal's law. This says Pascal's law. When brakes pedal is pushed, it exerts the force on the master cylinder. It will exert the force on the master cylinder. This is the master cylinder, which increases the liquid pressure in it, which will increase the liquid pressure. This is the liquid inside this. The liquid pressure is transmitted equally throughout the liquid in the metal clear pipes. The liquid will be exerted in all directions, and equal amount of the pressure will be generated throughout the liquid. So in equal metal pipes to all the piston of the other cylinders, due to the increase in liquid pressure, the piston in the cylinder move outward, pressing the brake pads with the brake drums. The force of friction between the brake pads and the brake drums stops the wheel. So in this example, you can see how there is a liquid inside this. Whenever the brake driver uh, push the brake pedal, it exerts the pressure on the master cylinder, and this pressure will be equally transmitted in both wheels, equally transmitted on on here and here. All the pipes equally exert the pressure. This is the application of the Pascal's law. So